So, in today's lecture, I will describe an example of a fully polynomial time approximation scheme or FPTAS, and today's problem is subset sum problem. This problem has two inputs, a set of integers which we could assume to be a1 to ak, and another integer t. A subset sum refers to the sum of the integers of some subset of S. So, let me describe the problem, the decision version of this problem. The decision version says that find a subset of S whose sum is equal to T. And if no such subset exists, then inform that it does not exist. So, here is find a subset with sum equal to T, else inform that it does not exist. But of course, we are doing approximation and we want an optimization version. So, in this case, we want to compute the largest possible subset sum, not exceeding T. So, such a number will always exist. Of course, in most cases here you will not find a subset which is adding up to T, but here we are asking for the largest sum. So, we want to maximize a subset A over the subsets of S such that the sum x in A subject to the fact that this sum is less than or equal to T. So, this is the objective. Clearly, if you find that the answer is equal to T, then the corresponding decision version is solved, because you know that here is a subset that adds up to T. Otherwise, this value will be always strictly less than T. Okay. So, suppose the optimum value of this, optimum value is say denoted by Z star, that is the largest subset sum less than or equal to T is Z, and computed value is Z, the computed value through the approximation scheme that we will discuss. Then we are going to show that Z star divided by Z, which we know clearly has to be greater than or equal to 1, we will show that it can be bounded above by 1 plus epsilon for any choice of epsilon less than or equal to 1. For any, this is what our goal is, that is why we call it a scheme, that we can compute the result arbitrarily close to the optimum. Okay. So, now let us see how do we proceed to solve this problem. What we will do is, first we will describe an exact algorithm, which obviously will take exponential time. The reason being, there are 2 to the power k subsets. If we generate each of them, we compute each subset sum and then pick the largest, we are going to have an exponentially large amount of time. but then we will modify it and devise an approximation scheme out of it. So, let us begin with an exact algorithm. We begin with defining a sequence containing just the 0. So, we will view these PIs as sequence or lists, and in the beginning it contains just 0 in it. One remark, any of these numbers is 0, then we can ignore it because it does not really add any value. Any number is exceeds t, in that case we can ignore it because that will definitely give you a subset exceeding t. So, every number has to be strictly between 0 and t. Now, we are going to generate for I equal to 1 to k all the subset sums in the following fashion. What we will do is we will generate this incrementally, that is to say Pi will have the list Pi will have subsets subset sums of all the integers from a1 to ai. So, Pi will contain everything that Pi minus 1 contains, and then we will also add to them ai. So, this is since we are maintaining a list, for the purpose of keeping this as a list is because we will essentially, in implementation this is fairly straightforward, we will, or rather sorted merge. So, we will keep this as a sorted list. So, to emphasize that, sorted merge, we have L, or rather P I minus 1, Pi minus 1. We are going to merge these two lists, Pi minus 1 and Pi minus 1 plus ai. What this refers to is that we add ai to each member of Pi minus 1 and generate another list of the same size as Pi minus 1 and merge these two lists. Okay. Now, clearly what you notice is that if this contains the sum of every subset of first I minus 1 integers, this will contain then the sums of every subset formed by a1 through ai. Now, at this point the only thing we have to do is eliminate those numbers which exceed t. So, we will simply put that remark, remove every element of Pi that exceeds t. So, we clean up and now ready to go for the next iteration. At this point, when we have Pk, which means we have got a list containing every subset of these integers which do not exceed t, we are going to take the largest among them, the largest element of Pk. So, it is fairly straightforward and returns Z star. So, this is a simple algorithm to exactly compute the answer to the problem. So, what do we do to make it an approximation algorithm which runs in polynomial time. Clearly note that here we have generated all the to the power k, actually not explicitly generated the subsets, but we have generated the sums of every subset, all the to the power k. So, this obviously takes exponential time. So, the way we can improve this in terms of time is that we maintain smaller lists. So, in order to reduce the size of the list, this is the way we will proceed. Suppose the numbers in the lists are over the real line spread like this. In other words, there are clusters of subset sums in list Pi somewhere. We will try to reduce or replace these by fewer numbers. So, there are too many numbers here, over here and here. So, what we will do is that suppose you have a number alpha at any in the list at some position, you have a subset sum equal to alpha, then we will not allow any number in between alpha and alpha times 1 plus delta. Now, here delta will be chosen suitably, later on we will see how to choose it, but it is a number which is positive and much smaller than 1. So, we will not keep anything in between here. As a result, what will happen is that the ratio of jth number and j minus first number will be greater than or equal to 1 plus delta. That way we will control the population size of this list. So, we will essentially copy this, but on top of it we will add one more condition here, that trim this list so that we do not have numbers which are very close by. So, let me now repeat this. Approximation algorithm is L0, again starts with a 0 for I equal to 1 to k. Li is sorted merge of Li minus 1 and Li minus 1 plus Ai. Okay. Trim Li. Now, this is the step that will basically do this, and then remove the larger numbers, everything greater than t. Remove numbers greater than t from Li. So, the only difference is this step, the rest is the same, and now we will determine the largest element of Lk. And return it. So, this is it. This is the only modification we have made in the algorithm. So, now let us write down what trim does. Trim of a list L, let us say this list is x1, x2, xp. Then we start with an L prime equal to the list containing only the first integer of L. Then for I equal to 2 to p. Oh, there is one more thing I want to say, that is the last integer we have added to the list. So, we begin with last equal to x1, this is the last integer added to the list, and then for I equal to 2 to p. Then we see if xi is a greater than or equal to maybe last times 1 plus delta. So, then it is far enough. Then we are going to add it. Then L prime is appended with, we add this xi to the list and set last equal to xi. That is all. So, we have removed numbers which are very close, and now we can just return L prime, return L prime. This is what trim will do. Okay. So, the question now is, finally, how good is the number finally we have computed, namely z. So, let us start the analysis, and first of all we will try to prove that by suitable choice of delta we will find z star divided by z bounded by 1 plus L. Okay. So, our first claim, and the main result in the analysis is this, which says for each x in Pi there exists a y in Li such that y is less than or equal to x, and that is less than equal to y times 1 plus delta power I. This is trying to show that we do have a number for every number of the original list, there is a number which is close by in the computed list Li. Okay, so, let us try to prove this. We will prove using induction. So, the base case is trivial. Base case is that actually two lists are same, is that P0 is equal to L0. So, there is nothing to prove, both of them are equal to the list containing only 0. So, now induction step. So, let us assume that the claim holds for I minus 1 and we want to prove for I. Let us take two cases. So, let me say sub case or case rather, case that x that we have chosen from Pi belongs to Pi, but was new number, Pi was not present in Pi minus 1. That means this is a number which is the result of a number in Pi minus 1 plus Ai. Okay. So, there exists an x prime in Pi minus 1 such that x is x prime plus Ai. So, we have this. Now, since x prime is in Pi minus 1, we will exploit the induction hypothesis. So, from induction hypothesis, there exists a y prime in Li minus 1 such that y prime is less than equal to x prime less than equal to y prime 1 plus delta power I minus 1, because we are working with list I minus 1 on Pi minus 1. So, we have this. So, y prime plus ai is less than equal to x prime plus ai, which is same as x rather, and that in turn is less than equal to y prime 1 plus delta power I minus 1, that is less than y prime plus ai times 1 plus delta power I minus 1. So, this is simply adding ai, and this is a trivial inequality. Now, notice that this number y prime belonged to L I minus 1. So, when we were building Li, this must have been, this number y prime plus a must have been created, and maybe it was eliminated for being too close to some already existing number. So, due to trim, there exists a y double prime which finally stays in Li, such that y double prime is less than or equal to y prime plus ai, and that in turn is less than y double prime to 1 plus delta. So, this is guaranteed the way trim works. We must have, it is possible that y double prime is y prime plus ai itself. So, let us relate y double prime with x. Using this inequality, I have y double prime which is less than equal to y prime plus ai, that this is the inequality that we have used. Okay. That in turn is less than equal to x from this inequality, which is less than or equal to y prime plus ai into 1 plus delta power I minus 1. And now, I use this part of the inequality, that y prime plus ai is bounded above by y prime y double prime 1 plus delta and 1 plus delta power I minus 1 makes it 1 plus delta power I. Okay, so, this is exactly what we wanted. Y double prime is less than equal to x, which is less than equal to y double prime 1 plus delta power I. This is the case. Now, let me take the second case, the case of x already existing in pi minus 1. So, x belongs to pi minus 1. This is the second part of this. So, once again, from hypothesis, from induction hypothesis, there exists a y prime in Li minus 1 such that y prime is less than or equal to x, which is less than equal to y prime 1 plus delta power I minus 1. This we get from the given fact, which holds for I minus 1th list. Now, what do we do from y prime? Now, note that y prime was in Li minus 1. So, in the formation of Li, so recall Li, which was formed by Li minus 1 and Li minus 1 plus ai. both, and then we trimmed it. So, y prime was present here, so it might have gone into Li, or there was a number too close to y prime. So, there exists a y double prime in Li such that it is less than or equal to y prime, which is strictly less than equal to y double prime 1 plus delta. So, we have this guarantee from the trim algorithm. Okay. So, let us combine this and this inequality. We have y double prime less than or equal to y prime, which is less than equal to x, okay, and that in turn is less than y prime 1 plus delta power I minus 1. This inequality further bounds it as y double prime 1 plus delta power I. Once again, we have this inequality that we wanted to prove over here. So, that establishes the claim. So, now once we have the main result, let us see what are the consequences. The corollary of this result, one of the corollaries rather, is that Z is less than or equal to Z star, which is less than equal to Z 1 plus delta power k. Okay, this is easy to prove. The first claim is trivial because this is the largest element of Lk, this is the largest element of Pk, and Lk is a subset of Pk. So, clearly this could be larger than this. Okay. Now, since Lk is contained in Pk, rather Lk contained in Pk, Z has to be less than equal to Z star. This is trivial. Now, from our result that we have derived, as Z star belongs to Pk, there exists a y in Lk such that y is less than equal to Z star less than equal to y 1 plus delta k. And Z is the largest element of Lk. So, we have y less than or equal to Z. We already have argued Z is less than equal to Z star, that is less than equal to y 1 plus delta power k, and again y is less than equal to Z. This inequality says that it is Z 1 plus delta power k. So, this is this establishes what we wanted to prove. Well, it indicates that Z star is not too far from Z. The gap can be at most 1 plus delta power k. So, now it is a matter of choosing the right delta, so that we can establish our objective, namely Z star by Z is bounded by 1 plus epsilon. Okay. So, after this, let us choose delta k equal to epsilon by 2 by k, epsilon by 2k, and then we are going to use some inequalities. So, our claim is, or I would say so we have a claim which says if this is this, then then we have what we wanted, 1 less than equal to z by z star by z, which is less than 1 plus epsilon. So, let us prove this. Okay. Well, what we have from the above result, z is less than or equal to z star, that is bounded by z 1 plus delta power k, power k. Okay. That we will now claim is less than, okay, let me first of all substitute this, which is z 1 plus epsilon by 2 by k power k. This is epsilon. All right. So, now let us use this inequality, e to the power alpha is greater than 1 plus alpha, the expansion of e power alpha is 1 plus alpha square by 2 factorial alpha cube 3 factorial and so on. So, this is there. Let us use this and take this as alpha. So, based on that we are getting, let me just, okay, this is z e to the power epsilon by 2 by k whole thing power k. So, I have replaced 1 plus epsilon by 2 k by e to the power epsilon by 2 by k, which is same as z e to the power epsilon over 2. Now, there is another inequality for numbers smaller than 1, e to the power beta by 2 is less than 1 plus beta for beta less than or equal to 1. So, this is another inequality which allows me to further bound this by z 1 plus epsilon. So, that is what we wanted to establish. So, by choosing delta as epsilon by 2 k, we have found a number z close enough to z star. So, that establishes the correctness of the approximation. So, the question now is, what is the time complexity, what is the space complexity? Well, what you noticed in the algorithm is that we are actually scanning through the list and we merge the list and its variant where we add ith integer. So, the entire time it takes is proportional to the length of the list in each iteration. So, what is the goal? So, to analyze, we need the length of ith list. This denotes the number of elements in the list. All right. Now, let us try to look at this real line, say this is 0, 1, which can be written as 1 plus delta power 0. Then we have 1 plus delta power 1 and so on. 1 plus delta power j, say we go up to 1 plus delta power alpha, which is equal to t, the largest number that we are interested in. So, the entire range from 0 to t is split into these intervals currently. Now, suppose there is an integer in let us say in this interval in the list Li, then we know that the next integer has to be this times 1 plus delta or larger. Hence, this cannot fall inside this interval. So, the next number has to be outside this interval, must be beyond this point clearly, because that number times 1 plus delta has to be greater than this. What we conclude is that inside the interval we cannot have more than one number in the list. Hence, the total number of elements in the list cannot be more than the number of such intervals, which is alpha. So, we can say that the size of list is less than or equal to alpha, and that is nothing but you just take the log. So, let us just log of t base 1 plus delta, that is the alpha, which we will write as log natural t divided by log natural 1 plus delta. Okay. This is important to notice that although this is log natural, log base 2 of t is the size of t, which is one of the inputs. So, we are now dealing with a number of the order of the input size, okay, which is important. This is a constant. So, the time complexity must be of the order of k times this. Remember, this number is independent of I. So, k times this number. The reason is we are scanning through these lists in each iteration, there are k iterations, is of the order k times mod of Li, okay, mod of Lk rather, which is the largest of them, and that is of the order k times log natural this log natural 1 plus delta. Okay. Now, if we want to further simplify this, we will use another inequality which says that x divided by 1 plus x is less than equal to natural log of 1 plus x. This is easy to prove. If you set x equal to 1, x equal to 0, this is 0 and this is 0 because log 1 is 0, and then you differentiate both sides and you notice that the derivative for both are positive, but this is less than this. So, this grows slower than this. Let me now use this inequality. So, we get Li to be less than equal to natural log t log 1 plus delta. So, that comes on the lower side in the denominator. We get 1 plus delta divided by delta. Okay. That is equal to 1 plus 1 over delta. Delta was epsilon by 2k, 2k by epsilon natural t, let me 2k by epsilon. So, time complexity is now equal to k times 1 plus 2k by epsilon times natural log of t. Now, let us take a look at this. K is one of the input parameters. Log base 2 of t is the size of the largest integer. All other integers are of course less than or equal to t. Other parameter here is 1 over epsilon. Notice that 1 over epsilon is occurring by itself, not as an exponent of some number. Hence, this is a fully polynomial time approximation scheme, FPTAS. The space complexity well, at any point in time we keep one list, and while constructing the next list we might need space which is about at most 4 times that. So, this is only of the order of the size of Li, which is, as we have seen, nothing but 1 plus 2k by epsilon log natural of t. So, that completes the argument that it is indeed a FPTAS complete. Okay. Next, we want to give you a very small example of a randomized algorithm and its analysis. So, our next problem is a randomized approximation of 3 set. You are aware of the problem of satisfiability, that you are given a Boolean expression in conjunctive normal form and you want to check whether it is satisfiable or not. 3 set means that that expression, let us say expression E is say it has got n clauses, every clause has exactly 3 literals in it. So, given this the expression restricted in this fashion, also it is hard to determine whether it is satisfiable or not in polynomial time. So, our goal is to solve this problem, but we are going to work on its optimization version. We want to compute an assignment of the variables which satisfies maximum number of clauses. Obviously, that will solve 3 set, but we are going to approximate that. I am going to show that a very trivial random assignment will satisfy a very large number of clauses. So, let us do the this assignment. So, our algorithm is, the first step is for each variable assign value 1 with probability half. One half, and with 1/2 probability it will be assigned 0. Please note that all these assignments are independent, all variables are assigned independently. So, now in the first step we have generated a value assignment and of course return this, return the computed truth value assignment. Okay, so the question is, how good is this? Well, let us take a look at any clause. The clause has 3 literals. So, the probability that first literal, remember a literal is a variable or its negation. So, with probability 1/2 this can be false, with probability 1/2 this can be false, and with 1/2 L3 can be false. So, the probability that a clause evaluates to false or 0 has to be 1/2 power 3, because every literal must evaluate to 0 for this clause to be false. So, probability of a clause to evaluate true is 1 minus 1 over 2 cube, that is 7 over 8. Okay. So, this clause evaluates to true with very high probability, 7 by 8. So, now we want to compute the following. Remember, this is a randomized algorithm, so we can't have exact ratio of the evaluated number to optimum number, but we will have an expectation of this. So, expected number of clauses evaluating true divided by maximum number of clauses that can evaluate to true, evaluate to true. This is the number we want to show is greater than or equal to some number. Note that this is less than or equal to, no, this is greater than or equal to expected number of clauses evaluating to T. This is given under computed truth value assignment. To true under computed assignment. Note that the total number of clauses are n, so that has to be an upper bound to this number, and since the truth value can be computed, because these are all separate clauses. So, each evaluates to 1 with probability 7 by 8. So, this itself is greater than or equal to sum the probability of it a given clause evaluating to 1, we multiply that by 1. So, 1 times 7 by 8 I going from 1 to capital N divided by N, which is nothing but 7 by 8. So, what we notice is that even with a simple truth value assignment computed completely randomly ensures that at least 7 by 8 clauses will be true on an average. So, that completes our discussion of the approximation algorithms in this series. Complete. Okay.